Okay. Today, we're going to go over a few things here and there, and then we're going to hit the ratio test. So first of all, a harmonic series. This is the quintessential harmonic series, but it's really anytime you're in the situation of a constant divided by something that is linear, where n is the variable of sigma is the variable. So if you see any constant over linear, you are dealing with harmonic. A harmonic series is a known divergent series. And you can see all those guys right there. But the thing is, there's this really cool way of showing that it's divergent that I want to share with you. And what it is it's a little bit about grouping. So the grouping is starting with the third term. We're going to group together the third and the fourth term. Then we're going to take the next four terms. So that's going to be 1/5. And we're going to group those together. And then we're going to double the number of terms we take. So we're going to have 1/9 until we reach 1/16. And then we're going to double the number of terms that we take from there. So I went ahead and just prepped what they have in the book, and I can highlight and everything what they've got. So what they're doing is they're looking at nth partial sums. And that's what I was meaning by the grouping. We're looking at grouping this by the nth partial sums that are 2 to the power of some number. I'm going to put in, I'll put an n, because they're using n further down anyway. So we're looking at nth partial sums where they are 2 to the n power. So starting with 2 to the 0 power, 2 to the 1, 2 squared, 2 cubed, and so on. Something super cool happens. And whoever noticed this pattern must have just been absolutely elated when they saw this. So what I want you to see first of all with S sub 4. 1/3 is greater than 1/4. That means that my fourth partial sum is greater than 2. Then, with S sub 8, we keep that idea. And I'm going to erase what I have here. Lunch, not COVID. I always feel like I have to explain it's not COVID when I cough. Okay, so we have that situation again that we had from the S sub 4 of 1/3 being greater than 1/4. But now we're taking 1/5 and 1/6 and 1/7 and noticing that all three of those are greater than 1/8. And what is 2 times 1/4 as well as 4 times 1/8? They're both 1/2. Pretty cool, huh? So this is a way to show that the basic harmonic series diverges. You keep doubling the number that you group together and find that that group is larger than 1/2. And if you've got infinity to go, you can continue finding twice as many numbers to group and see that that is also adding more than 1/2. And we do that forever. So just to see one more of these, basically we take the highest, not the highest, the smallest number, the last one, 1/4, and make both of these 1/4. And then we have two of them. The 1/8 is then the largest of those numbers. Sorry, not the largest, the smallest. What am I saying? Anyway, maybe I should just highlight. And basically, if we take all of these numbers and see that they are greater than the 1/8, the smallest of them, and then for the next batch, make them all 1/16, and there are 8 of them, we just continue to say 1/2. And that is greater than that particular sum. So the details are right there, and then I'm going to stop there. You can look at it later if you want to a little bit more, but come on, who thinks that's amazing? It's so cool that somebody saw that pattern. Now, the next problem I want to do with you is different from harmonic, and it's something that I think you should see, even though it's not necessarily showing up on the AP exam, but a certain part of it is on the AP exam, so hey, here we go. We are going to rewrite this formula by doing fraction decomposition, which you do have to know how to do. So, fraction decomposition. Here we go. I need to find the constant A, and I need to find the constant B. I first multiply both sides by the common denominator. And as I distribute over the addition, I get A times n plus 1 times cancels with the denominator, plus B times n times cancels with the denominator. And then I choose to plug into the n variable the zeros of their factors. When I plug -1 into n, I get 1 equals 0 minus b. So b is -1. When I plug in 0, I get 1 equals a plus 0, so a is equal to 1. And now I'm going to go back and I'm going to rewrite this. But now with this formula, where a is +1, and with b being -1, I'm going to write minus 1 over n plus 1. And now what we're going to do is we're going to start writing out the first few terms. Plug in n equals 1. And then next we're going to plug in n equals 2. Plugging in 2, I get 1/2 minus 1/3. Plug in n equals 3. 1/3 minus 1/4. And I can keep doing that. Does anyone see the lovely pattern that's starting here? And I want to point out that what I've written is the nth partial sum. Yep, you got it already. It's beautiful, isn't it? You have minus 1/2 plus 1/2, minus 1/3 plus 1/3, minus 1/4 is about to cancel with a plus 1/4. The one, I just realized I didn't write my subtraction sign right there. Silly. That needs subtraction. And then this plus 1 over n is going to cancel with the previous minus 1 over n, and everything in between just... So that means that my nth partial sum is 1 minus 1 over n plus 1. The infinite sum is the limit as n approaches infinity. And that approaches 0 as I head to infinity. So if I can get a real number answer to that limit, then that means my infinite series converges, and I additionally know what it converges to. Pretty cool. When this happens, they call this telescoping. And to understand why they chose the word telescoping, wait, the first problem isn't... Oh, hold on, I'm checking chat. For the first problem. Oh. You mean the harmonic series. The harmonic series has an issue that I warned you yesterday to be extremely careful about. And let me point out that issue because it's really important. The divergence test is only going to determine diverge. The contrapositive is true, but the converse is not necessarily true. So if you get that you are approaching 0, if your formula is approaching 0, that doesn't mean it converges. That means you look like you might converge. So how about you go ahead into... That's where I consider you've got a bunch of sigmas trying to get into club converge, and the door person says, yeah, you look like you're small enough. Go ahead and go in. But then they enter this area that's not quite club converge yet, and they've got to then find a table who will be able to determine whether they converge or not. And so this is just like the door person that says, okay, you can go look at a variety of tests and see which one is going to figure out whether you converge or diverge. And we're actually, for the harmonic series, going to have another way to explain the diverge as well. No, yeah, that was where we were at. So just to bring that up. Now, telescoping. I want you to think about how long ago series was probably looked at. So before the computer time. Yes, you are going to have to say by a certain test. What is telescoping? Why would this be called telescoping? the second example that we looked at. For this problem, you actually wouldn't have to say telescoping. Did someone have a hand up?
Yeah, I was just kind of wondering, for this, when you say converges, do you have to say like converges by like geometric series test or something?
With this one, it actually converges by definition because of the fact that the definition of converge is that the limit as n approaches infinity of the nth partial sum exists. So why do you think I'm telescoping? Think a couple hundred years ago. Why would they have... No. You have to really think about what they used. Think about what they used. They called it telescoping. Okay, picture, like, say it's the 1700s and you're at sea and someone's pulling out a telescope. Think about the telescope they're pulling out. Aw, none of you are seeing the... Yes. They had those funny little things that they would have to go pulling it out. Okay, I need to find a picture of that because now it's bugging me, but I can't just search without. Never mind, I can't. So basically they get out this thing that looks like this, but then they pull it out and it's like and then back together. I don't know if that drawing does it justice. There you go, extends and retracts, yeah. But anyway, that one's really cool to take a look at. So now that finishes up section 11.2 and all the little things in there. If you looked at your homework assignment, I gave you a few problems in section 11.2 for homework. It's a mixture of what we've done already with section 11.2, and I'll leave it at that. Now we move on to, I'm going to skip over to section 11.6 with the ratio test, because the ratio test is the most used test of any of them. You are ready to learn it at this point. You're ready to learn it as soon as you learn about a geometric series and the converged divergeness of a geometric series. And as textbooks go through all the different tests, they wind up using tests that you would never use for those problems because the ratio test would take it. So I don't want to waste your time with problems that you would never use the particular test that they gave, and focus on the problems you would need them for, where the ratio test won't work. So let me explain to you the ratio test. To explain it, I have to start with what we understand about a geometric series. In a geometric series, if you divide any of the terms by their predecessor, you will get R. Now, what the ratio test does is it looks at what is the ratio of a term and its predecessor as you go down a little farther. And they actually absolute value it for the sake of being easier, because a geometric series converges if the absolute value of r is less than 1. Now, if as you near the end of your infinite series, if you can go all the way down there and you find that this is heading to a number, this ratio is heading to a number, that means that in the end, it's beginning to behave like a geometric series. It's not exactly a geometric series, but it's behaving close to it. And if I'm getting an answer that is less than 1, if the absolute value of that ratio is heading to a number that is less than 1, it is behaving like a geometric series and it converges. Now, that's just an explanation, but it's not a proof. The proof is in your textbook if you want to read the full proof, but the explanation provides more insight than the proof necessarily provides. And it's the insight of understand you're creating something that behaves like a geometric series near the end. So this would give you a converge. Now, if you take that same limit and you find out that you get a number that is larger than 1, then it's behaving similarly to a geometric series that very much diverges. And the reason you need proof and not just an explanation of what I'm giving you is you need to make sure mathematically that your insight is correct. And it turns out that if you get 1 as an answer, when you're dealing with a geometric series, you get diverge if you have equal to 1. But through proof, we find that the ratio test is actually inconclusive if we get 1, because we can find examples where the answer is 1 using a convergent series, and we can get an answer of 1 using a divergent series as well. We can find an example of each where we get an answer of 1. That means that this is inconclusive. So here's what I want you to picture. You see a bunch of sigmas lined up wanting to get into Club Converge, but they first have to be checked to make sure they actually do converge. So the door person looks them over and decides if the formula itself is heading to 0. Because if it's not, just don't even bother. Please don't make our lines longer. Go somewhere else. Find Club Diverge. It belongs in Infinity Land. But then what I want you to consider is those people, those sigmas who are let in, are not going directly into Club Converge. They're going into a place where they need to find the right desk to, say, pass the registration test. Ooh, maybe it's where they get their temperature check. Relating to current times and having to have your temperature checked before coming on. Never mind. Anyway, but basically you're not quite in Club Converge yet, but once you enter this entryway, basically, you have a bunch of tables lined up and you need to pick a table to go to. And these are each tests to determine converge diverge. Now, it might be that is more than one table who will be able to meet your needs. If you were a sigma, let's say you are harmonic, you do get past the door person. But you decide ratio test, I love ratio test. I'm going to use ratio test. So you get in there, you wait in line. 2 hours later, you get to the front of the line to have them go, I'm sorry, I'm inconclusive. I don't know. You need to find another line. And then the poor little Harmonic Series is like, but I don't know which line to choose. And it's like, I can't help you. All I can tell you is I'm not going to work for you. So find another line. So it's kind of like the old-fashioned DMV thought of, but they've actually gotten a lot better where, they make sure you're in the right line. Especially with COVID, we don't want to breathe air longer than we need to. Okay, so, never mind. You do want to breathe air, just not contaminated air, COVID contaminated. Never mind. So it's very important to understand that if you get equal to 1, it was a waste of time to look at the ratio test. It tells you nothing. And if you are turning in your work on determining converge diverge, you want to just completely cross it out. It was useless, and it isn't part of what's helping you determine converge or diverge. So you don't want to even mention it if you got an equal to 1. Now, I'm going to show you how to do this test through this example. And this example is from section 11.6. And here we go. You're going to start by writing limit as n approaches infinity, and you're going to have absolute value. Now let me mention real quick, if I'm absolute valuing, is -1 to the n a bit pointless? So what that means is if you're in a multiple choice problem, ignore it. But if you're in a free response problem, you really should write it down. Now, keep in mind what I'm putting in this limit is the n plus 1th term divided by the nth term. However, do you really want to have a fraction in a fraction? Do you want to see a fraction of 2 fractions? How can you avoid having fraction divided by fraction? What can you do to that little denominator? Oh, wait. There you go. Fraction over fraction. What can you do to the denominator? Yep. Go. Multiply by the reciprocal. It's who you divide by that you're multiplying by the reciprocal. So what you're going to do is you're going to look at the formula and you're going to plug in n plus 1, even including that -1 to the n, because we want to properly do the ratio test if this is a free response problem. And then for the n cubed, it's now quantity n plus 1 cubed. 3 to the n is now 3 to the n plus 1. And then times, and now I'm just going to reciprocate that formula, because that formula is a sub n. So the denominator, 3 to the n power, is now the numerator. The n cubed was the numerator, now it's to the denominator. And technically the -1 to the n is in the numerator. I'm just writing it down for the sake of it, just to be fully looking at the whole thing. Now, I'm going to quickly get that negative out of the way so that we can see what we're actually working with better. And you can do this as soon as you have written it down. The absolute values just go out. Now, the first thing is, what can you do algebraically to simplify this? Some of you probably see the answer to the limit already, but I want to make sure that you're clear about the algebra that is going on. 3 to the n plus 1 is really 3 to the n multiplied by 1 more 3. So you can cancel the numerator multiplication by 3 to the n and the denominator multiplication by 3 to the n. And I'm going to now rewrite what we have. You don't have to rewrite as profusely as I'm doing right here. I'm doing this to make sure you're very clear on what is happening. So now, you should be able to know the answer to the limit at this point. You can painstakingly go through some algebra, but it's not necessary. You should realize that when you expand n plus 1 cubed, you get a polynomial where the leading term is n cubed. In the denominator, you have 3n cubed. If n is approaching infinity, you're treating this like you did with the horizontal asymptotes before. The numerator's n cubed overtakes any lesser degree terms adding or subtracting if I'm heading to infinity. So this turns into a ratio of n cubed over 3n cubed, which is 1 to 3, and I get 1/3. So once the limit is answered, then is that greater than 1, less than 1, equal? Make sure you say it is less than 1. That is extremely important in a free response exam, that you state it's less than 1, and then you are allowed to say that it converges by the ratio test. And that's how you do it. You can solve these limits quickly or slowly. The limit has to be used once you reach something that looks polynomial-ish. And I want to clarify that as you look at this, and hold on because I'm annoyed with something. There. Now I'm no longer annoyed with it. Okay. I want you to notice that n cubed is a polynomial. 3 to the n is not a polynomial. It is exponential. In fact, if the 3 to the power of n didn't have that numerator, this would be geometric. When a function looks like an exponential expression, you are dealing with a geometric series. When a function looks like a polynomial, you're dealing with something else, which we're going to talk about more later. But that mixture causes this to not be a geometric series. But the ratio test allows us to work with that mixture we can algebraically cancel the 3 to the n plus 1 with, we can cancel that function away when we are looking at the ratio. But the one that looks polynomial is not going to just simplify. That one needs the limit. And when you hit that point, you're using everything you've learned since when you began doing rational functions right after polynomials, and you looked at horizontal asymptotes. It's exactly that. Once you get to that point with the limit. So that's how you do a problem. And I'm going to say a few more things. But first, I want to point out to you with your homework assignment. Let me find. So with your homework assignment, you are doing a few problems from section 7.2. And then I want you to go over to this page. This, if you actually look deeper into what this person has done, it is amazing. There's a copyright on it, but I checked the terms of use. I am allowed to give you a link. It's just credit due where credit due. This is made by a Paul Dawkins from Lamar University. This site is amazing. It's been around for several years. You can see 2003. So it's really good. You might want to look through it. But I'm assigning you these 4 problems. And what's really nice is you can click on solution. And then you can see the whole thing all at once. You can see just the answer. Or you can get like, how do I start this? And push start solution. It'll help you out with step 1. So it's really great to work with. So 4 problems from there that you're going to try on your own. Now, going back to what we are learning, there's something that I want to let you know about the ratio test, because who wants to stand in a 2-hour line for the ratio test just to be told, I can't help you? The test fails here. You want to know which series to not bother the ratio test with. So don't bother the ratio test and we're going to learn later how to deal with these issues where it won't work. Don't bother it when you see something that looks like a rational function. And I'm going to quote rational functions only. Now, I'm quoting it because you might have some extra bits like, hi, I'm a -1 to the n that rational functions don't have. But what I'm saying is, here's an example of something to not bother the ratio test with. If I take out that -1 to the n, do you see that that looks like a rational function? Polynomial over polynomial. Don't bother the ratio test if all you have to offer are polynomials. Because if you take a moment to think about it, if you plug in n plus 1, that's not going to change the degree of your numerator denominator. If you reciprocate this, it will flip the degree of your numerator denominator. And when you then multiply this with the reciprocal, you have same degree issues. And you're going to have the same leading coefficients on top of that. You're going to get 1. And if you need me to show you a little bit more, let me... Ooh, I know. I'm going to throw a number over here, right there. And how about let's put a number there. Okay, if I replace n with n plus 1, and then I multiply by its reciprocal, if I'm looking at a limit as n approaches infinity, then I am looking at my largest degree term. Now, this numerator's factor, largest degree term, is n to the 1 power, and it's being multiplied by a 3. Further down the line, n to the 5th is a largest degree term within its pack, and it is multiplied by 4. In the denominator, n to the 5th power will create the leading term of its particular fraction denominator. You have to bring the 4 with it, and then leading term again. So take a good look to see that the ratio test will not work with rational functions. And I'm going to add in also that throw in a square root, and it's going to be the same situation. So if you see rational functions or maybe rational functions with roots, ratio test is not going to help you. Now, why did I move over to the ratio test? I've been talking about finding interval of convergence of those power series. We learned a bit about power series, the Taylor series and everything. And then you saw that for some of them, it looked like those polynomials only mimicked functions for a short bit. And that's actually the domain of that power series. To find the domain of a power series, most of the time, you are actually going to begin with the ratio test. It is the most important test of all of these tests that we are going to learn, and it's very important to take a look at it early on. Also, I'm bringing it to you early because, like I said before, I don't want you wasting time trying to use something that a ratio test will deal with easily on the tests that are coming. And I want you to also take note, I'm starting you off with some of the most important tests. These are the things you want to think through first before you head to the tests that are coming up. So if you want to check, is it a geometric series? You can save yourself a lot of grief if it is. Ratio test, very, very top of the line with, I want to think through if the ratio test is going to work with it before I turn to some other tests. Recognizing a harmonic series is a nice quick divergence. And don't forget, the door person, the divergence test is also important to clear out sigmas who are obviously diverging. And that's what you have so far. And then in the next few days, we're going to go through sections 11.3, 4, and 5, and then make our way back to 11.6. And those are going to have a variety of tests. Some of them are used quite a bit. I'm going to tell you who doesn't get used tremendously, who the last resort is, and all that. But that is it. So I should stop recording. If I can find, there we go. Nope, that's actually not it. I don't think you want to look at that, the pictures of yourself.